Welcome to SumLab. Today we're in for a bit of theory, looking at the nature and behavior of electrons. This will quickly get us quite deep into the structure of atoms and also give us some insight into the shape of the periodic table. And then, all going well, we can do a bit of an experiment to illustrate some of the theory. First up, I want to dispel a myth. If you think of electrons as little dots that somehow orbit the nucleus of an atom, I want to crush that idea completely. Now, to be fair, it is sometimes convenient to describe electrons in this manner. You will often see textbooks do this, good textbooks even. You'll probably hear me describe electrons this way from time to time, and we can even use the image of electrons as dots to predict the shape of molecules. The thing is, the notion of orbiting dots might be an okay description, and even a suitable for prediction, but it is a lousy explanation. It fails to explain why electrons behave the way they do. All the chemistry rests on the behavior of electrons, so the better our understanding of that behavior, the better our grasp of chemistry in general. So, if electrons are not orbiting dots, then what are they? One of the great scientific discoveries of the early 20th century is a phenomenon known as wave-particle duality. In other words, objects can be thought of either as waves or particles, and the smaller the object, the more appropriate it is to think of it as a wave. Physicists at the time were concerning themselves with light and photons and X-rays and beams of electrons and streams of neutrons, and observing what happens when you smack these at surfaces or into substances. And they were making observations of reflection and refraction and diffraction and absorption. Pretty much all of these observations could be explained okay using a particle model. They could also be explained using waves, so which is better? It turns out that waves have a bit of a party trick. It is possible for a single wave to pass through two spaces simultaneously. So if we see this kind of thing happening with electrons, then it stands to reason that waves are a better explanatory model. By the way, where exactly is that wave? Does it even have a precise location? If someone said there was a fish swimming in the wave, would you be able to locate the fish? Or would there be an element of uncertainty about it all? Let's take a look at a pretty standard kind of wave, a vibrating guitar string. This is a nice simple one to choose because A, it is one-dimensional, and B, we can observe it easily, both visually and by the sound it makes. Now we notice that the string vibrates laterally between two extreme positions, here and here. And if I'm just interested in that upper position, I find that it is a well-known mathematical shape. It can be modeled using a sine function, y equals sine x. Actually, not quite true. The string has a particular length, let's call it L. The function then becomes y equals sine pi x divided by L. So far, so good. The next thing we discover is that this string has more than one possible mode of vibration. If I place a finger right in the center, I can prevent that part from moving, and I set up a waveform of a different shape. We might draw it like this. And the mathematical function becomes y equals sine 2 pi x divided by L. By putting my finger in a different place, we get a third mode, y equals sine 3 pi x divided by L. And in general, we might describe the wave shape with the formula y equals sine n pi x divided by L, where n is any natural number from 1 up, and indicates the number of bumps that fit into the length of the string. So, on the guitar, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, n equals 7. Something else to note about these waves, they vibrate at a particular frequency, that is, a particular number of vibrations per second. It is not obvious just from the diagram, but this wave has twice the frequency of this one. That is, it does twice as many vibrations per second, and this one here has 3 times the frequency, and so on. You can't see it easily on the diagram, but you can hear it. High frequencies give higher notes. So what? Well, it turns out that energy is related to frequency. Let me demonstrate with this cheap whistle. This is the sound it makes. But if I blow harder, that is, apply more energy, I force it into a higher energy mode. a vibrational mode with a higher frequency, and that higher frequency is actually the result of a higher N number. So we've arrived at an important conclusion. The mode of vibration can be designated by the parameter N, and the number N gives us some information about the energy state of that waveform. Higher N means higher energy. The next party trick that waves have: two or more waves can occupy the same physical space. I can draw it badly like this, but you get the idea. What is critical is that the two superimposing waves have a different parameter N, otherwise they are not two different waves. Interestingly, it is this superimposing wave phenomenon that causes different musical instruments to have different tone. The application to electrons is, well, maybe not completely obvious, but we can try anyway. Electrons in an atom occupy the same physical space, superimposing or overlapping one another, but they have different modes of vibration and hence different energy states. And this is what makes them distinct. They have different parameters to describe their mode of vibration, although we will soon see that we need more parameters than just N once we move past one dimension. Before we start looking at 2D and 3D, I want to modify our guitar string model a bit. On the guitar, the ends of the string are fixed, but imagine we had a string of infinite length, and also imagine that the further away you got from a central point, the thicker and stiffer the string became. What would happen? Well, the string would still be able to vibrate, more in the middle, but less and less as you got further away. You would end up with a wave without a well-defined edge. Where is the boundary? Where exactly is the edge of an atom? Electrons, at least in theory, extend to infinity in all directions, but we have a zone where the activity is concentrated. The precise location of the electron cannot be determined with any precision, not because we lack the measuring equipment, but because the electrons are by nature fuzzy beasts without that clear boundary. This uncertainty about their precise location is something you may have heard of as the Heisenberg uncertainty principle, and it is for this reason that electrons are sometimes referred to as clouds, or we sometimes speak of the probability of an electron being detectable in a certain space. These things don't always play nice with our intuition. Okay, electrons are obviously not one-dimensional, so let's see if we can develop this a bit. Imagine a two-dimensional surface like the skin of a drum, just the one end of the drum. I don't want to consider the interaction between two electrons just yet, although that might be interesting to return to another time. Or perhaps another 2D surface, like a puddle. Let's see if we can perhaps visualize the possible modes of vibration here. We could imagine the skin of the drum pulsating, the middle vibrating backwards and forwards, and the cross-section forming the typical sine wave. Or we might find higher modes of vibration where we form concentric circles of raised and lowered regions. You should note while we're here that some parts of the wave shape are positive or raised and some are negative or lowered. This happened with the guitar string too. If we wanted to, we could make the positive and negative regions different colors, and we'd end up with a sort of archery targets kind of a diagram. But that is not the only shape that is possible. Imagine sloshing water in sort of a rotational fashion, and again we might get different modes of vibration happening. There might be one wave chasing itself around in a circle, or two, or three, or any number. So you can see with two dimensions we need more than just one parameter N to describe the wave. We need one parameter to describe the shape, and another one relating to the frequency or the number of bumps to fit in the space that is vibrating. Come to think of it, we might need something else as well. That last wave shape, the sloshing in the glass, it could go either clockwise or anti-clockwise. We could use an additional parameter to describe the spin. And of course, we could have two superimposed, one going in each direction. Indeed, we could have any number of these waves superimposed and all occurring simultaneously in the same space. This actually happens on a drum skin, and is why drums generally don't sound like they're playing any particular note. Next is 3D and actual electrons, but before we get there, we might need some help visualizing what's going on. If we go back to our guitar string formula, the string is lying on the x-axis, and it vibrates laterally, moving backwards and forwards in the y direction. This is cool, because we can see it. But who said it had to be a movement in y? Sound waves in air are transverse waves. The mass looks the same, but the displacement is in the x direction, which is a lot harder to see. But maybe instead of movement or displacement, we had a change in temperature, or magnetic field strength, or electric field, or some other thing. The wave vibration is a pattern in some quantity that can store energy but does not need to be movement into another dimension. So we can consider an electron as a waveform in 3 dimensions without worrying about having a 4th dimension for it to move into. Right, 3 dimensions and electrons. Let's just dive right in and look at the mathematical equation. Now if that beast does not freak you out, then you have a better brain than me. Suddenly they got crazy. And this is a simplified version. But before we get completely overwhelmed, let's see if we can spot some things. The last equation that we looked at and understood used y. This one uses psi. Psi is the Greek letter used for the wave function and refers to, well, who cares? The point is that we don't need a 4th dimension. Another thing to note is that this is happening in 3 dimensions. Our last equation used x to refer to a position on the guitar string. Now I'm used to x and y and z coordinates to describe a position in 3D space. That is not what is used here. Instead they've gone for spherical coordinates, a radius r and 2 angles. Apparently this is easier. And remember how we use the parameter n to describe the mode of vibration? Well, you can find it here too. But in 3D we need more than just one parameter. We have 3, n, l and m. And finally we have a note about spin. This equation does not show spin, but it is a thing. Just as we can have water sloshing in a glass in both directions simultaneously, so we can have 2 electrons with the same n, l and m numbers, same energy, same vibrational shape, but having opposite spin. So as well as n, l and m, we can have an s number to designate electron spin. So what do these things look like? Remember how I drew a shape, or envelope, which was the extreme position of the vibrating guitar string? And remember how we looked at a few different modes? Well, here is the same thing for an electron going around a hydrogen atom. Things to notice. 1. It is the same formula that we saw before. 2. And here we have it being called the probability density function, which we can think of as the proportion of electron activity that occurs in that space. 3. And here are a bunch of pictures showing the shapes for the different vibrational modes. In brackets we have the n, l and m numbers in that order. Number 4. We have positive and negative areas on each of the diagrams shown by the different colors. Some of these pictures are like the concentric circles we got on the puddle. 5. You should note the fuzzy edges. There is no clearly defined boundary to any of these. And that might be just about it for this video. This might seem technical and the application of all this theory unobvious, but actually we've come a long way and quite quickly. One last thing before we leave. The pictures we've just seen are for a hydrogen atom, where there is only 1 electron. The good news is that the maths and the shapes we get are almost identical for every other element. It is nice to have at least one thing that works out easily without adding complications. That's it for now. See you next time in the lab.